Let f be a polynomial in x of degree n, where the coefficients are real numbers. Then, f can be factored in the form shown here, where the numbers alpha, beta, gamma, and so on are called the roots of the polynomial, and in general, they're complex numbers. The numbers a, b, c, and so on are called the multiplicities of the roots, and the sum of the multiplicities is equal to the degree of the polynomial n. For convenience and without loss of generality, let's set the coefficient an equal to 1, just so we don't have to carry it around everywhere with us. Now that we have the polynomial written in this form, let's use the product rule to take the derivative with respect to x. It's clear that the derivative of f is a polynomial in x of degree n minus 1. If we divide the derivative of f by f itself, then we find the expression shown here. F prime over f is what's called the logarithmic derivative, and that's because if we take the logarithm of f and then take the derivative, we can use the chain rule, and the derivative of log f is just the same as f prime over f. The logarithmic derivative of a polynomial is what's called a rational function, which means that it's the ratio of two polynomials. What would really be nice is if we could get rid of the denominators on the right-hand side of this expression. And if it's not immediately jumping out at you, it really should. We can use the residue theorem. All we have to do is integrate f prime divided by f along a closed curve C in the complex plane, and then divide by 2 pi I. Let's see a picture of what's going on here. Since the roots of f are complex numbers, we can plot them as points in the complex plane. Then we're going to draw a closed curve C which surrounds some of the roots, and this is going to form the boundary of a closed domain in the complex plane. And we're going to integrate the logarithmic derivative of f around this closed curve with a specific orientation. Now we're going to draw tiny little circles that surround each of the roots of f which are inside this domain, and then connect those tiny circles with lines to the curve C. And we're going to use this new curve to define a new path of integration. Since the expression that we're integrating is continuous along these lines that we just drew, the parts of the integral going in opposite directions along each line actually cancel out. And since we're integrating a rational function which is well defined everywhere within this region, we can use Koshi's theorem, which says that the integral along this path is actually equal to 0. And so the original integral that we were trying to compute is just the sum of the integrals taken along the tiny circles in the opposite sense. Each of the terms that we're integrating in this expression are rational functions which are called simple poles. They're called simple poles because of how simple it is to directly calculate the integral for any expression like this. We can just use the parameterization for a tiny circle centered at the point alpha in the complex plane, plug in the values of z and dz, and then take the integral from 0 to 2 pi. And then we immediately find that the answer is 2 pi I. The numbers a, b, and c are what are called the residues of the rational functions we just integrated. In other words, the conclusion is that for any given polynomial, the logarithmic derivative of that polynomial is a rational function that has simple poles whose residues are the multiplicities of the roots of that polynomial. But the thing is, that was way too ridiculously easy, and it's very mysterious, and I'd like to really understand what's going on here. Where does the 2 pi come from? And what's going on with that I?